Hi there, I'm Brendan Bradley from the University of Canterbury. I'd like to thank the organisers and the ISSMGE for the opportunity to deliver this lecture entitled Prediction of Earthquake-Induced Ground Motions Using Simulation Methods and Their Validation Against Observations, where I'll talk about the topic conceptually as well as my own direct experience applying these methods principally in a New Zealand context. There's four main sections to this presentation, and I'll start with some introductory and definition remarks. There'll be various comparisons between what are frequently called empirical and physics-based models used in ground motion prediction. And so just to clarify the specific jargon, in this context, empirical methods predict a quantity of interest based on direct observations of that quantity. For example, if we want to predict peak ground acceleration obtained from a future event, we make use of observed values of peak ground acceleration in historical events. The process of model calibration essentially validates these methods to the extent that the observational data is similar to the predicted scenario, whereas in contrast, physics-based models simulate the salient or underlying physics of the phenomenon of interest from which we extract simulation results and obtain specific quantities. So for example, ground motion simulation using a three-dimensional crustal model and kinematic description of the earthquake source results in acceleration time series from which we can compute intensity measures such as peak ground acceleration. Unlike the empirical methods, the calibration of simulation occurs at the constitutive level, the definition of the three-dimensional crustal model, the definition of the kinematic earthquake source, and therefore in and of itself doesn't ensure that the simulation results have validity. While there's often this exaggerated dichotomy between these two methods, in reality advances occur due to progress in both approaches, and I'll talk more about this later in terms of how they can be used. Just to make some of those abstract concepts a little bit more concrete, here's an example comparing ground motion versus weather. So in an empirical context, ground motion prediction might be depicted such as shown on the upper left-hand slide, where we have observed values of spectral acceleration as a function of distance, and each one of those points represents observations, with the black line and its dashed values indicating the model prediction, including its uncertainty, whereas the physics-based ground motion prediction in the upper right-hand panel illustrates the simulation of wave propagation. Drawing the parallel in a weather context, the empirical equivalent would be prediction of temperatures on each day in the month of May based on, for example, the last 100 years of observations of predicted daily highs and lows for each one of those days of the year. And so by definition, those empirical methods, to the extent that we ignore climate change for the moment, does provide an unbiased prediction of what we'd expect in May in 2022. But you can see from that bottom left-hand panel that there is quite significant uncertainty in those predictions. In contrast, in the bottom right, we obviously make use of meteorological models to predict weather for the coming days. And clearly, with a good understanding of the physics of the atmosphere, we can make use of observational data and our understanding of that physics to provide higher precision predictions than we can with empirical methods. So there is precedent in other disciplines for this progression from empirical to physics-based methods, but naturally it requires a good understanding of the physics and suitable observational data to validate those methods and also provide the boundary conditions for them as well. That also leads to the notion of an inference spiral, as coined in an earthquake context by Jordan. And this really proceeds as shown here, where we may first address some initial problem by having some observational data, and with that observational data alone, develop some simple empirical model. We need to verify the implementation of that model. The extent that will be onerous will depend on how simple or complex the model is. We make use of that model to predict some future event or possibly retrospectively predict events that have been observed. And then we make use of new observations to validate that current model. That's in an ideal context where we have true prospective validation. With those additional observations, they indicate some deficiencies in the model, either significant deficiencies or minor deficiencies, that allow us to improve the overall model theory or make adjustments to its underlying parameters. And then we proceed round this spiral again, where we need to re-verify the new model, predict more future situations, and make use of more observations. So this cyclic process is really a key for us to make improvements in our quantitative methods because of the fact that often with simple models, first order changes can be made, but second order imperfections in the theory can't be seen because of the size of the first order errors. So as those first order errors are rectified, then what previously were second order errors now become the new first order errors. So this gradual process of model improvement rather than expecting any fundamental changes or advances due to one component alone. So in that context, why physics-based ground motion prediction, and in particular, why now? What are the key tailwinds that are enabling this technique to be practically useful at this stage? Well, one of the first things is the declining benefits that we're seeing in predicting ground motions using empirical methods. So what we're looking at here in this plot is standard deviation, so uncertainty in the prediction as a function of year. And we see that, generally speaking, with a significant amount of scatter, there's a relatively flat line in our ability to actually reduce that standard deviation with time. In fact, as some more recent studies have been collecting more and more data, we've seen some of the complexity in those observations that prior studies didn't necessarily appreciate to the fullest extent. And so actually there's a potential increase in our uncertainty just because we're capturing it to a better extent than we did previously. The second is a significant increase in measurements. Globally, we're seeing something on the order of about a 4.5-fold increase every decade. However, when we look in a little bit more detail at the disaggregation of those observations, we see that most of the increase actually comes due to small amplitude motions. So it's just increase in sensitivity of instruments or increase in the number of instruments that we're observing. And so really a key determinant of advancing these predictions is how can we best learn from small amplitude ground motions to improve prediction of what we ultimately care about, these large amplitude motions. And then finally, of course, computing resources. We're seeing an exponential increase in available computing resources, but then also science is catching up with that quickly as well to harness the size of those computing increases. And all of those improvements are allowing advances in each of the constitutive components of ground motion science. So our description of the earthquake source, our description of the so-called path, the 3D crust and which ways propagate, and then the zoomed in version of that, what we often refer to as side effects, because of our improving understanding of geotechnical and geophysical properties. So as we make advances in all of those areas, really in order to demonstrate the predictive capability, we need to validate these simulation methods against observed data. And I won't go through, because of time, the actual granular details of the simulation methods, other than to say the examples that I'll present are using relatively mainstream approaches within the ground motion simulation research field. So some examples from the 2010, 2011 Canterbury and 2016 Kaikoura earthquakes. Naturally, it's important to emphasize that all of these results make use of the same methodology and input parameters, and so the only thing that changes is the actual rupture models for each earthquake. Just to provide a graphic illustration, here's a simulation of the 2016 Kaikoura earthquake, magnitude 7.8 earthquake off the east coast of the South Island of New Zealand. It was a very complex rupture with multiple faults rupturing in a general south to northward pattern. And in these ground motion simulations, because we described the earthquake source to its full complexity, we can capture events that have such an substantive complexity. And so, of course, one of the challenges is describing the complexity of that seismic source, and while we can't do that definitively in advance, we can consider different hypotheses for what ruptures might occur in the future. And then the resulting output of these ground motions is a time series at each point in the simulation domain. And so what you can see in the upper left-hand panel of this animation is 5 different buildings that are subjected to the simulated ground motion, in this case in Wellington. From those simulated ground motions, we can compare them with observed ground motions at each of the strong motion instruments shown on the slide in triangles, and then perform waveform comparisons, such as shown here, for different locations in the near fault, epicentral, and in particular Wellington region. Or more quantitatively, we can compare intensity measures, such as you can see here for peak ground acceleration or 3 different vibration periods of spectral acceleration. All of these figures shown as a function of distance. And in particular, the green points represent the observations, the red points the simulations, and the black line and its dashed lines the median and 16th and 84th percentiles of an empirical model. So while there's a lot of scatter in the observed data, as we expect, we also see much of that reflected in the simulation data as well, and in particular, looking at the bottom right-hand panel, seeing the really large variation in ground motion amplitudes at a distance of about 100 kilometers, and that large variation is also captured in the simulations due to that south to north rupture propagation, which we can model in the simulations, which is much more complicated to model using empirical methods. So for each observation simulation pair, we can take the logarithm of the ratio, and that's typically what we refer to as the residual, and then plot the distribution of those residuals as a function of spectral acceleration vibration period. So we can do that for each individual event and get a trend or a conclusion, as you can see here, in this case for the 2016 Kokoda earthquake. Based on the single event, what sort of inferences can we draw? Well, one of the main challenges is from one event alone, it's not clear how much of the misfit between observations and the underlying prediction is due to an imperfect simulation method, or the method is close to reality, but the crustal or rupture models don't have the right values. And so it's based on a limited data set alone, we really can't do that, and we need to extend to significantly more events and more observational data. So over about the past 8 years, we've been gradually focusing on the main events in the past decade in New Zealand, but then also expanding our horizons to look at small magnitude events, moderate magnitude events, and large magnitude events. And so here's just some examples of past studies that we've looked at in the Canterbury region, for example, as well as in the upper South Island Wellington region, based on the 2013 series of earthquakes that happened in that region. And so broadly, we're making use of up to 2,000 events above about magnitude 3.5 that have been recorded since 2003, when dense instrumentation was deployed throughout New Zealand. So really what we're sort of seeing, coming back to that earlier slide, is a trend where empirical methods, we talked before about that gradual decline in our ability to improve them, or actually a slight increase as we quantify that uncertainty a little bit better. And then this general trend with physics-based methods where, although they've been deployed since the 90s, and potentially depending on how much you draw parallels with current methods versus some of their precursors, even into the 80s, the theories for those methods were developed, but our ability to constrain the inputs for those methods meant that we had quite high prediction uncertainty. And then gradually, as the realism of those simulations has improved, our ability to predict has improved, and therefore the uncertainty has come down. And so here I plot in a couple of red points some of those studies that we've done, in particular around the 2020s, and we're seeing about now this crossover between our ability with simulation methods to obtain lower prediction uncertainties than with empirical methods. Now, of course, this is a schematic plot, so in reality, the so-called crossover where simulation methods are providing improved predictions than empirical methods is going to be a function of geographic region, because the quality of the input models in terms of the Earth's crust or the seismic sources is going to vary region by region. And then some features of the ground motion are inherently easier to predict than others. So measures such as peak ground acceleration or duration may not be as easily predicted between the two. Although there's still a long way to go in terms of improving the validity of these simulations, they're already now at a point where we can start to contemplate their use in seismic hazard analysis, and the way that they substitute into the seismic hazard analysis equation and calculation is relatively straightforward. We have models that describe the earthquake rupture forecast, all the different earthquake sources in the region, and for each earthquake source we perform ground motion simulations as opposed to just using conventional empirical methods, and we couple those two together to obtain probabilistic seismic hazard analysis outputs. So here, for example, you can see a map of seismic hazard values for a certain exceedance probability throughout the New Zealand country. We can compare these results from simulation-based methods on the far right with empirical methods in the middle, and then look at the ratio of those two like we would with any set of quantities shown on the right-hand side here. And then also it's important that we don't have to consider one empirical approach or simulation approach. We can actually make use of multiple approaches. It's conventional in seismic hazard analysis to use so-called logic trees to account for alternative model interpretations and provide a subjective weighting to each of those interpretations. And so presently, multiple empirical ground motions are conventionally used in seismic hazard analysis, and each of those multiple ground motion models are given a weighting, but we can think of it that the cumulative weight of those multiple empirical models currently represents 100%, and there's generally given 0% weighting to simulation-based approaches. So gradually over time, we'd expect a non-zero weighting to be given to simulation approaches, and then the overall weighting will be a function of that predictive capability of the different modeling alternatives. So this provides a sort of smooth transition pathway where we don't need to jump from 0 to 1 in adopting these simulation methods, but we can gradually increase the weighting that we're giving them as we have quantitative illustrations of that predictive capability. So there's several ongoing challenges for advancing ground motion simulations, and I want to touch on 3 of those in particular. The first one is how we can make use of validation and examination of residuals for region and site-specific prediction advancement using that inference spiral construct that I was mentioning earlier. So I described before some of the different data sets that we've been looking at, and here's just a few more details of those. For events that we often refer to as small magnitude in the 3.5 to 5 range, we have on the order of about 500 events in New Zealand and about 5,000 ground motions. For events that are moderate in magnitude, 5 to 7, fewer events, obviously 75, but about 2,000 different ground motions. And then larger magnitude events, but in particular events that have been recorded where we have significant event-specific details such that we can actually develop event-specific finite fault models. Currently in New Zealand, there's 14 such events. They cluster geographically, as you can see here, with most of them in 3 regions, Fiordland, Canterbury, or the sort of Kaikoura-Marlborough region. But one thing that we find in particular is for the largest or complex events, such as the 2016 Kaikoura earthquake, the uncertainty in actually describing the kinematic rupture for that event tends to dominate the overall simulation uncertainty. So then our ability to gain inferences in the ground motion simulation itself is less about the ground motion simulation and more just about the uncertainty in the seismic source. So somewhat paradoxically, although we care the most about large magnitude events and the large amplitude ground motions that they cause, it's actually the small and moderate magnitude events that tend to give us the most insights for validation of simulations. For each of these events, we can start to dig into the differences between observation and prediction a little bit more. Briefly, the mathematics for this is we have our observed ground motion in logarithmic space, we have our simulated prediction, and then we decompose the residual, or the difference between those two, into some bias term across all events, a term that varies from earthquake event to earthquake event, a term that varies from site to site, and then a sort of leftover residual after we deduct those systematic terms. And so looking at one New Zealand-specific, New Zealand-wide data set on the left-hand side here is an illustration of the overall bias, where ideally a value of 0 would be obtained as a function of vibration period for response spectra, or some other measures such as PGA and PGV shown on the right-hand portion of each panel. And so we can see here where black represents our conventional empirical model, that with our modified ground motion simulations based on learning from observations, we're generally doing a good job in getting results that are close to 0, either similar to or slightly better than what we see with the empirical models. On the right-hand side is the standard deviation resulting from these predictions. So despite some of those apparent wins from the simulation methods, we're not really, at least with current simulation methods, seeing a significant reduction or any reduction in the standard deviation. And that's really because these simulation methods are not yet significantly region or site-specific. And so just one comment on data quality, comparing these figures on the left-hand and the right-hand side from two different studies, the right-hand one using only data in the Canterbury region, the left-hand one using the New Zealand-wide data set, we see reductions in standard deviation of about 10%, just due to the fact that we have better constraint on some of the observational data in that Canterbury data set. And so really those total standard deviations that we see are dependent on the events and the stations in which they're recorded. What is of significantly more value is some of the spatial variation that we see in model performance. So here's the average residual per event, or the so-called between event residual, plotted spatially. And you can see that there is geographic clustering of the positive values in red or the negative values in blue, which indicates some spatial variation in the earthquake source that we're not currently capturing. And we can do this comparison whether we use simulation methods shown on the left-hand side or whether we perform our prediction using empirical methods, and try and understand the correlation between those two to see what are the systematic things that both of these prediction methods are missing. And one of the obvious ones is trying to understand, is there a geographical dependence of the stress parameter, which indicates the amplitude of the high frequency ground motion. And so here's two different studies that we examined, and when we looked at the correlation between the stress parameter estimates for these studies with the between event residual, we did see a significant positive correlation, which does provide the opportunity to incorporate spatial variation in our predictions for these models, rather than just assuming that the stress parameter for all future events is constant geographically in space. We can do similar things when we look at site-specific residuals between our predictions, and in particular what we see is that we have very strong correlation between those residuals at high frequencies, in particular because both simulation and empirical methods tend to use similar approaches. Further digging into some of those results as an illustration, we can qualitatively group different sites. So in these four different panels, we're looking at four different types of sites. That's indicated in the upper left-hand corner of each of the panels. The grey lines for each panel show the site-specific residual for that individual site. The blue line represents the global bias across all sites, and the black line, the solid black line with the shaded region, represents the mean bias for this particular subset of sites. And so by looking at individual subsets, we can see where the overall bias for those deviates significantly from the bias across all sites, and therefore identify how we can make improvements to the ground motion simulations for these types of soil conditions. In a geotechnical context, performing 1D site response analysis is obviously of significant interest. So how do we couple these ground motion simulations with conventional site response analysis? The main challenge being that these ground motion simulations are performed on the order of hundreds of kilometers in regional scale, and often with a spatial discretization of tens or hundreds of meters, whereas often geotechnical site response analysis, that spatial discretization, at least vertically, can be on the order of 1 meter or so. So typically we can't capture the near surface soil properties with the resolution in the ground motion simulations themselves. So instead we perform the simulation without detailed site response in the first step. We then deconvolute the ground motion to the base of some reference condition within the sedimentary deposit, and then in the third step we actually perform convolution using now a much more granular representation of the site response. So as one example of this, we performed a study using 11 events from the Canterbury earthquakes recorded at 20 different sites. And one of the most significant components of this particular case study was that we had repeated observations at the same 20 locations over these 11 different events. And that really allows us to understand the systematic features between event to event, and so whether we are actually improving our prediction using 1D site response analysis as opposed to just conventional VS30 based site amplifications. What we saw, in just a quick summary, was that at some sites where we do actually have very pronounced site response, we see some improvements when we make use of the 1D site response analysis, what's referred to here in the legend as wave propagation analyses, compared with our empirical VS30 based approach. So for these two sites on the left hand side, you see that the systematic residual, or the overall bias for these sites, is closer to 0 for the black line with site response analysis than it is when we use empirical methods in red, or when we neglect site response entirely as shown in blue. Whereas for many of the sites there was really no difference difference whether we used empirical VS30 based approaches or 1D site response analysis, and sometimes even worse performance using these site response analyses. The last thing I wanted to touch on very briefly is making use of explicit uncertainty incorporation in these simulations and how we propagate that uncertainty through the ground motion simulations. So we really go from the situation of having a single event with a single ground motion simulation and compare that with a observation to now having many different ground motion simulations representing uncertainty in the parameters or the constitutive models of the ground motion simulation. And so we've done some initial work on this, as have others, in the Canterbury region, where we focused on uncertainties in the source parameters, but this is a field with significant amount of work ahead of it as well. Another significant challenge is distinguishing between parametric and modeling uncertainties and whether you consider components of those to be so-called apparent aleatory variability or epistemic uncertainty, because then a lot of the parameters will have some parametric correlation between them, and also will have some uncertainty in estimating those values from past observations, and we need to be careful to make sure that we don't double count some of that propagated parameter uncertainty with the misfit uncertainty against the observations. So to conclude, in summary, ground motion simulations are increasingly being used in seismic hazard analysis. To further see increases in adoption, we need much more systematic and comprehensive validation. Ideally, they would be the same data sets that are used for the development and calibration of empirical methods, and to try and untangle the misfit between whether it's associated with the simulation method or the constitutive properties of that simulation. And then we expect to see pronounced regional or site-specific variations in that predictive quality. Explicit treatment of uncertainties will be a common occurrence as we go forward, and really just to emphasize that these same foundational approaches towards simulation advancement have carryover lessons for other subdisciplines as well. Thank you very much for your attention.